All right, good morning, students. Welcome to the first day of hybrid learning for you. Unfortunately, in AP Psychology, we can't do hybrid learning or hybrid pacing, I should say, because we have a lot of information to get to. So I want to make another quick tutorial on some of the higher level brain functionings that we're going to look at. We had started with what we consider the old brain or the lower level brain, and now we're getting into higher level, higher operation brain systems. This is a slide that you would have seen yesterday when we talked about the limbic system and really that kind of emotion control center. And now we're going to continue on with really kind of how humans are different than every other mammal because of our brain. And we'll start with what's known as the cerebrum. Now, the cerebrum are just the hemispheres that make up the majority of our brain. So when we talk about the cerebrum, we're talking about so I brought a little brain here with me. I wish you could see this at school. By the way, this is right back here, the cerebellum, the little brain. So this is what we consider like the two hemispheres, if you will. And by the way, when you're doing your project, if you are showing me the celebrity brain, I would like to see this view, like this outside view. Sometimes it's called the lateral view, but I'd also like to see this view, kind of the inside, if you will, the cross-section view. So when we talk about the cerebrum, we're talking about the hemispheres that make up the majority of our brain. This is like the gray matter, if you will. But covering this hemisphere is what's called the cerebral cortex. Now, the word cortex, cortis means bark. And so think of the cerebral cortex as like the bark of the brain, like the thin covering of the brain. In fact, I even have a piece of paper here. This is about, if we stretched it out, if we made it kind of how it is, I'll show you. This is about how big our cerebral cortex would be. Billions and billions of cells, but it's like the size of a sheet of paper, very, very thin. But this is like the ultimate control center. In fact, if we did this and made it, that's kind of like how it would cover our brain. The folds are incredibly important. And we'll talk about the folds here in a second. So within this cortex, it's made up these glial cells. And remember when we talked about glial cells before, those are those kind of fatty cells that support the axon. And so the cortex itself, the cerebral cortex, is made up of these billions and billions of cells that really support and make the cortex. It's the glial cells that absorb the excess neurotransmitters when the neuron has excess neurotransmitters and it gets absorbed back into the neuron, through the axon. It's the glial cells that are doing that. And so the cortex, this covering, is extremely important because it is like the control and processing center for our brain. But remember, it's paper thin. It's very, very thin, this thin bark covering the brain. So if you can imagine on my little brain here, it's just this very thin covering of the brain, but it's incredibly important. So now we have some lobes. Now each of these hemispheres, like this, we've got two hemispheres, right and left hemisphere, is divided into lobes. And these lobes are, we have 4 lobes. And they're separated by these fissures. You know when I just crumpled that piece of paper to kind of show you what the cerebral cortex would look like? Those folds in there are what make up what's called the fissures. Now, fissures are these, and the deeper your fissures, the more complex learning ability you have. And so actually, they have done studies of people's brain who are highly intelligent, very high IQ, and they see deep fissures or deep folds kind of coordinating in conjunction with high level intelligence. So let's talk about the lobes of the cortex. Now remember, the cortex is like the gray matter, right? 85% of our brain is the cortex. And so when we talk about how these are divided up, we'll start with the frontal. If I look at this, right, here's the frontal lobe right here. So this would be like the front of my brain. Your frontal lobe is right here. Now the frontal lobe itself is divided, but really mostly for our purposes, we mostly really just need to know about the frontal lobe itself. It's right behind your forehead. It's very much involved in speaking, muscle movement, making plans, judgments, like thinking ahead, what if scenarios, if I do this, what's going to happen. So the frontal lobe is extremely important. I don't know if I mentioned it to you, but your frontal lobe as a teenager is not actually fully developed. Your frontal lobe won't be fully developed until you're about 25 years old. So there's a lot of speculation about, so let's say for instance, legalizing marijuana. Should marijuana be a legal substance? And a lot of people say it's absolutely no more detrimental to your brain or worse for your body than, say, alcohol is, which is legal after age 21. Well, what we know is that while both marijuana and alcohol are not really on the level of dangerous to your brain, they're pretty much about the same. Under the age of 25, both of them are pretty detrimental. Like, you're going to do a lot more damage before age 25 to your brain than if you waited for your frontal lobe to fully develop. So hold off on using drugs or alcohol until you are, obviously, there's about at least 21, but maybe even a little older, because that's where we see a lot of degeneration happening before it has time to mature. The parietal lobe. The parietal lobe is right here at the top of our head. So probably from about this area on back. So this whole kind of crown of your head, if you look like right here, this whole top side is the parietal lobe. On this one, you can see it's right here in yellow. I wish I could send this around the class so you could see this a little bit better. This is for sensory input and touch. So like really anything you feel or taste. Well, yeah, I guess taste. No, scratch taste. Feel. Just go with feel. Let's just say feel. Sensory input for anything that you feel. In your body position, meaning do you know that your head, where your head is in relation to your feet? So for instance, if you do a cartwheel, think about how your body position is changing. Your parietal lobe helps you orient what's up and what's down. And so if you're doing a cartwheel, you come and you land on your feet and not on your head. That's the parietal lobe is helping to work at that. The occipital lobe. The occipital lobe is at the back of the head, and that's the lobe that's for your visual field, information on your visual field. So all the information that you take in, that you see, will be processed in the back of your head. You can see the occipital lobe right here. So again, if this is the front, and this is the back, the occipital lobe is back here behind your head. So all the information, it's pretty cool, all the information that comes in through your eyes gets processed back behind your head almost. So if you think your parents have eyes in the back of their head, you could probably be like, well, yeah, that's where their occipital lobe is. The temporal lobe. The temporal lobe is on right above your ears, right? Kind of like on this side, if you will. you see the temporal lobe right here in the blue, right above. Think of like where your temples are, right? If you've ever had a headache right at your temples, that's the temporal lobe. This is primarily for auditory information, which makes sense. It's right by the ears, which gets processed again on the opposite side. Remember yesterday when I talked about, or on the previous video when I talked about the corpus callosum? That's what helps cross that information to the other side of the brain. All right, so those are the 4 basic lobes. So I want to talk a little bit more in depth on the motor cortex. So the motor cortex is in your frontal lobe. This sends messages out of the body that help control your movements. Now remember, parts like the pons and the cerebellum help control movements, but this is more like voluntary movements that you have to think about, higher order, higher level movements. We're talking dribbling a basketball, or doing gymnastics, or driving a car, which actually takes a lot of motor movement. So the motor cortex is the part of the area in the frontal lobe, but closer to the back of the frontal lobe, if you will, to control voluntary movements. I think I have a video here, and I would like you to watch that. I'm not going to play it right now, but it's really interesting on people who have suffered traumatic injuries, or maybe for some reason have been born with paralysis or something like that. It's usually for people who had the ability at one time and lost it. And so the field of prosthetics is getting really, really interesting. And this video that I've embedded that I want you to watch is on neuroprosthetics. It's called reach planning. How your brain wants to make a movement, and then a robot does the movement for you. Is incredibly fascinating. And I truly want to say that if you are interested in psychology at all, and you maybe are interested in biology, and you do not want to go into like clinical work, you don't really want to work with people like in a hospital setting or a clinic setting, go into this area of research. It is definitely cutting edge with the technology we have now. A very booming industry, and one that could be extremely helpful to so many humans on Earth. Very, very interesting. So watch that video. The somatosensory cortex, I'll spit it out yet. The somatosensory cortex is, remember like the parietal lobe where I said it's a lot for the touch? The somatosensory cortex is where different parts of your brain, different parts of this cortex are developed or attributed to certain parts of your body. So for instance, if you ever get a tattoo, it might hurt in some areas to get a tattoo more than it would others. And it really kind of depends on where that falls on the somatosensory cortex. So look at page 73 in your book, that figure 3.14. You'll see kind of how much is devoted, how much of the somatosensory cortex is devoted to each part of the body that could take that incoming message, that incoming touch sensation. It's very, very interesting. I think about how important it is to understand touch, say, on your arm, as opposed to maybe on your cheek. So it, depending on the body part, is depending on how much devotion it gets to the sensitivity of touch. If we were here today together, we would do a little finger touch demonstration where I would, or you would, we'd have a volunteer, and I would put like a certain number of fingers on your back and ask you to tell me how many fingers, and I would just kind of like lightly touch. Well, it's really, really hard on your back to figure out how many fingers. Am I touching it with 2 fingers? Am I touching it with 3 fingers? That's actually a very hard thing to differentiate. So it receives all these incoming messages, and so the more sensitive it is, as I said, the more area in the somatosensory cortex is devoted to it. So make sure you watch that video on the motor cortex as well. All right, and finally, some of the other association areas. This is also a video that I'm going to need you to watch. It's a short one. It's a crash course video. We all love John Green. Oops, sorry, my mistake. These are definitely for higher area, higher association levels, meaning higher brain functioning. These are also areas in the cortex, you know, in the gray matter, but they're found in all 4 lobes. If we talk about the frontal lobe, we know that if there's damage to the frontal lobe, for instance, because this is such a high functioning area, we have problems with judgment, we have problems with planning and organization and thinking ahead, but it's also very important for personality. If there's damage to the frontal lobe, it can alter personality. And really probably the most, not probably, it is the most famous case study of damage to the frontal lobe came in this guy over on the very right named Phineas Gage. Now, Phineas Gage, and you'll listen to it in the video, he was a railroad worker, and he literally, you can see this picture right here, he got a spike, a railroad spike, went through his head, like up kind of like through his head, almost through the eye socket and out. And he lived. Like, it was absolutely amazing that he lived. And this is in like the late 1800s. But everybody said, and you'll hear this on the video, you know, afterward, he just wasn't the same Phineas. You know, he was kind of a different sort of guy before the accident than after. But it wasn't because of, you know, the traumatic effects that he had suffered in the accident. It was because his brain was changed. His personality was really altered. We especially see in case studies of sociopaths and people who suffer from severe mental illness like schizophrenia. It's in the frontal lobe that we see the most damage. There's a lot of correlation between frontal lobe, misfiring, damage, if it was trauma, and personality, and how mood and judgments are made. So I think we're going to do one more slide, and this will be the end. So the parietal lobe. Remember when we talked about the parietal lobe? We talked about it's for touch. Like, certain parts of the parietal lobe have more in like the somatosensory cortex, right? This is in the parietal lobe, and it stimulates our sensation for touching. So I want you to think about this. Don't move it, but think about moving your tongue. Don't move your tongue, but think about moving your tongue. Or, okay, don't move your fingers, but think about the motion of moving your fingers. That's the parietal lobe. Could you feel your tongue moving even though you didn't actually move your tongue? Or could you feel your fingers wiggling even though you didn't wiggle your fingers? That is this sensation. And again, if something happens and we lose those sensations, sometimes it's called phantom pain, where let's say, for instance, we see this a lot in victims who have suffered from IED, they've lost a leg or something in a mine accident or an IED or something like that, they let's say they lost the lower part of their leg, yet it still hurts. Like they don't have a leg anymore down there, but they can still feel that leg. Like they can still feel it, or they still feel pain, or they still feel like, oh, I got a tingling sensation or something like that. Really, really interesting. So you kind of believe it's happening, just like the wiggling of the fingers, but you didn't actually wiggle your fingers. And now I'm thinking about wiggling my fingers, and I can feel what it's like. The temporal lobe. We know if we have damage in our temporal lobe, especially in things like a stroke, that's where we see it the most. Obviously, if we have damage, we might lose our sense of hearing to an extent. We'll talk a lot about the types of hearing loss later. But for instance, in a stroke victim in the temporal lobe, we see that stroke victims sometimes will be able to, let's say for instance, describe what their spouse looks like, but they couldn't come up with their husband or wife's name. Like they couldn't come up with their spouse's name, but they can describe who they look like, what they're wearing, things like that. They just couldn't come up with a name. That identity is almost like disrupted. In Broca's area, Broca's area is on the left temporal lobe, and if there's damage to this area, it would disrupt speaking. So the way I like to think of Broca's area is think of Mrs. Brock. Juniors, seniors, it doesn't matter. Mrs. Brock does what's called orals. So I think of Brock and Broca. Mrs. Brock does orals, and that's when you literally have to talk about those questions, essentially on the Constitution and everything. If you can't talk, if Mrs. Brock can't talk with you, it's because maybe you've had damage to Broca's area. So always think of Mrs. Brock speaking, talking. And she's on the left side. If we're walking down the hallway, oh, that's not a very good example now, because now we're going the opposite way. But pretend we're coming from the office down to Mrs. Brock's room. She's always on the left side of the hall, and that's Broca's area. Wernicke's area. The damage to this area would disrupt our understanding. Wernicke's area is more on the left side, but it's closer to the frontal cortex. It's kind of almost in between the temporal and the frontal cortex. And damage would damage to this area would disrupt your comprehension. So like you could probably speak, but the words would be like jumbled and wouldn't be able to understand. You could hear, but you literally can't figure out what the sentence structure would mean because there was damage to that comprehension and understanding in the brain in this area called Wernicke's area. All right, that's it for the day. I want to stop there. It's already been a long video. Catch up with you next time. Bye.